Hello everyone, and welcome back to some more reverse engineering and learning with a bit more of some exploit exercise in this one from Pointer Overflow CTF. Challenge is called A Gilded Lily, and it hints to something about Heartbleed as well as something to do with RUP gadgets. But that's alright. This was a fun introduction one, so I'll link it below and you can try it for yourself. When you run it, it just says Heartbleed Bug Simulator waiting for a request. Type some stuff and doesn't really do too much. There's no way to tell what it does, but that's okay. So I've already solved it, but I thought I'd step you through how I solved it and some things I learned along the way. So I've opened it up in Gidra, and we have a couple of things here. We could see that introduction that we were given, and then we can see here a scanf that looks for a number and a string separated by a colon here, and then sends a response where we have a call to write, the buffer that things were written to, that our input was written to, and a number of bytes. And if I've got the man pages open here, and we can see what arguments are required. So write 1 here is so we're writing to the file descriptor, standard out from this buffer, and the number of bytes that we put in there. So straight away we can see that gives us some sort of exploitation where there's no bounds checking to what we can write out in the application. So this allows us to leak information, which is good. And from here, what can we do? Well, the first thing it suggests is that we could look at doing some sort of RUP gadget or use RUP tools, as it did say there. So that means if we overwrite the return address, we could inject a RUP gadget or RUP tool. So if you do RUP gadget binary exploit 2.bin, and then I think it's RUP chain, this tells us all sorts of information. So it gives us, first of all, it lists through all the different types of RUP gadgets. And if you're like me, you can't really understand what all these do. So it does provide you some helpful tools when you use the RUP chain generation. So it tells you things, gadgets, where gadgets are just little bits of assembly where you can move instructions to certain places. There's a few gadgets or pieces of assembly that have syscalls. And this works together by just redirecting to, these are all sections of code in the binary. So if you overwrite the return address to point to here, you can execute this and then keep chaining these things together to execute multiple things. So we've got syscalls, number gadgets. And then from here, it tells us to build the RUP chain to actually get ourselves a shell. So it looks like we just pack these gadgets, add all these increments to this register, and then we try a syscall. So this essentially is our shell code to execute. But there is a problem with this binary. We can see here this long 10 value is set to some value from the binary, and there's also a check here to check if local underscore 10 is still equal to that value. So on the stack, this sits between our variables, our other variables, and the return address, and this is a stack canary. So I've just pulled up a picture here just to illustrate what we found. So if we want to execute anything, we got to overwrite this return address, but we have our local variables here which we can read from and write, so we can edit those. But there's this canary that has to stay intact, because if this gets changed and overwritten to what's expected, we'll get a seg fault and the application will crash. Alrighty, so the next sort of thing to think about is if this sits between us and our return address, why don't we exploit this right here to actually find out what the address of the canary is, which we can't do, which is perfect. So I have a bit of code here. So in a nutshell, I've just set a breakpoint. It doesn't really matter about that. We're going to try read larger than the buffer size, and we're going to fill up the buffer just with A's. So 1032 is going to be full of A's, and then anything after that is just going to be other values. Hopefully we can get the canary out. So let's run that and have a look what happens. So I have that print statement on the lines down here. So the canary is going to be put into this variable. We're going to read all the A's that we put into the buffer, and then we're going to read 8 more bytes after that, and so hopefully we should have the canary. So we can see here, here's our input string. So we're going to ask for 1044 bytes, all the bytes, and then we're going to get this response where we get A's, and then the important part is we can see this canary here. So we're going to read these extra bytes, which is the one that is on the stack. So this local 10 value is what we're reading. So you can see here, the problem I had that took me a while is these values here look a little strange. We're used to seeing hexadecimal. We're having two letters here, so we can see 00, BE, C3, but then here in some places we get some strange characters like 9C, QN, XDD, things like that, which doesn't necessarily line up with what we see in memory. So over here, if we examine the memory of, where is it, RBP minus 0x8, we see some of these values here. So 9cc, 3 BE, 0. We can see some of that here, like 9cc, 3 BE, 0. Let's read some more bytes. So we can see that some of these values here, especially that's confusing, is this here. And the difference between this string here, this binary string here, and this out bytes is some of these values that we see represented as bytes here are actually the ASCII encoded, which is really strange. So this 0x71 is in here, but it's still encoded as a slash. But that's okay. So we can go through, read from that array, each of them, and just make sure that we get it in the right format. So this is to be interpreted as a byte of 2 characters at a time. And that's why we can see that out byte section over here, which looks a lot better and a lot cleaner to what we expect. So we can see like DF and then DD. It's just backwards here just because of the endiness, but that's all right. You can get the point across. Alrighty. So we've been able to successfully leak the canary. What have we got to do now? Well, we just have to take this canary and send another input, because once we send one input, the actual execution loop just keeps going. So as long as while 0 is less than number of bytes, so pretty much indefinitely, as long as we put a positive number. So we can go through a second loop of this application and try and keep the canary, or at least preserve the value of it. It's important to note that the canary does change each time we execute the program, so this wouldn't work if we leaked it and we had to start the application again, but that's alright. So now we've got to chain our things together. So we have to take our payload. We don't mind at this time because we want to stop the execution now that we have the canary. So, or at least overwrite the return address and continue execution of the program. So we're going to set our next input to be 0, followed by our buffer bytes to fill up this buffer. We're going to put the canary that we learned on top of there, and then we're going to have to overwrite the return address. So there is a bit of spacing here with this, so there's some extra letters in here, extra bytes, and that's just because the difference between the actual canary and the return address. You can, if you're not too sure how to do that, you can use cyclic to find it. So you'll just give the input of cyclic, like a long string of 100 characters where you have one letter and one that repeats, and that way you can find out when you step through it in GDB, you can see what return address it actually tries to go to. So you can see how many bytes padding you have between your input and the return address. But that's okay. So we have our 0, we have our string, canary, some padding bytes, and then P, which is at the start of the video I said, which was the ROP gadget, or the ROP exploit that we're going to use, and then we can send that. So I have it executing locally here, so we'll just continue to see what happens here. So the breakpoint is just at the comparison of the canary. So the breakpoint is around here. We can see we have this move instruction and this XOR address, this XOR instruction comparing. So we have that here, we're just before it. So we're moving the canary into a register to check, and we're going to do a comparison. So XOR our input with the actual canary to check it's right. Next instruction, and so we jump. Well, we don't jump actually. Alright, so we're good. Alright, and then we can see the return address here. Here. Just go next instruction, follow it, and it's right. We're executing our ROP chain, so that's okay. We'll just execute it on the remote. So I have the remote solve here. Before you do Python 3. Remote solve. Alright, we can see that now we have a shell, and we can successfully get the flag. Alright, that's all. So I hope you enjoy, and let me know if you have any questions. Happy to help. Thank you.